Welcome to the ChemDoctor, and the purpose of this video presentation is to explain to the viewer how the periodic trend, atomic size, works as we move left to right across any period on the periodic table. Now, formally stated, when we move from left to right across any period, the size of the elements decreases. To talk about why this happens, I am going to focus on the elements that are in period 2. Starting with lithium and moving left to right and terminating with neon. All right, now you'll notice, and what I've done here is provided you with the atomic numbers. You notice that as we start with lithium and we end with neon, that the atomic number is increasing. If you look at a periodic table, you're also going to see that the atomic mass increases moving left to right across any period as well for any of the elements in any given period. So the question is, if we have atomic number increasing and we also have the mass of particular elements increasing as we go left to right, how is it that the atomic size is actually going down? All right, so because this seems like it's a contradiction. Now, in order to explain why this works the way it does, it's really important for the viewer to understand that what actually lies behind this is the force of attraction, the electrostatic force of attraction between the electrons and the protons that are in the nucleus. And this is described by Coulomb's law. All right, and I know the minute I utter Coulomb's law, I risk putting most of you to sleep. So I promise we're not going to dwell on this very long. So force of attraction, right? So literally how hard we're pulling on the electrons, because what you need to remember is that the electrons are the particles that are on the surface of the atom. They are the particles that determine literally how thick the atom is, right? What its size is, because the electrons represent what we have or what creates the surface of the atom. The protons and the neutrons are in the nucleus, a very tiny, hard place that's got the vast majority of the mass. So the protons and the neutrons are not contributing to the size of the element. It is all about the electrons and how tightly they're being pulled towards the protons that determines the radius or the size of the element. So Coulomb's law states that the force of attraction literally between the electrons and the protons is going to be proportional to, and I'm going to make this really, really easy. We're not even going to use variables here. It's going to be equal to the charge that we have, the charge relationship between what's in the nucleus and the charge on the electrons divided by how far away the electrons are from where the protons are squared. So essentially, all right, let me be more specific here. My little squiggly means in proportion. I'm just going to abbreviate that. All right, and then the force of attraction, how tightly those electrons are being pulled on, will be proportional to the charge of attraction. That's going to be related to the protonic charge and the electronic charge, right? The charge on the electrons, the total charge that we've got of the protons divided by the distance the two kinds of particles are separated, or the square of that distance, the distance that these particles are separated. All right? So two things going on. We've got the charge in the nucleus, the charge on the electrons, the mutual attraction there, and then how far apart these particles are, that distance squared. Now over here on the right side of the screen, I've provided you with a schematic that you can use to visualize what I'm talking about here, because you need to remember that the energy levels are different distances away from the protons, excuse me. Energy level 1 is the closest to the protons, and as we move to the next energy level up, which would be energy level 2, the distance of energy level 2 from the protons is significantly greater than it is for energy level 1 electrons, and the distance away from the protons where we find the electrons in energy level 3 is substantially greater than what the distance is for energy level 2 or for the electrons that are in energy level 1. So you can see Coulomb's law when you look at this, because you're going to have, for any given atom, let's say we're dealing with lithium, then we would have 3 protons in here. So I'll add 2 more charges, and it's this charge that will be responsible for attracting the electrons towards where the protons are. And that force of attraction is going to draw those electrons in to a certain distance away from where the protons are. All right, and that's going to determine how large that atom is going to be. All right, now how do we? So there's a couple things, 2 things that we need to look at here as we go left to right across the table. The first is that we need to think about, as we move, say, from lithium to beryllium, what is the distance factor involved in adding the next electron? And then second to that, and of no less importance, is to ask the question, what's going on with the nuclear charge? All right. To do that, we need to also consider a concept that's called effective nuclear charge. And what the effective nuclear charge tells us is basically the charge, let me say it this way, the charge available to generate force of attraction on surface electrons. That's the way to think about this. How much charge do we have available that's actually operating on the outermost electrons? Because the outermost electrons are the distance that they occur away from the protons is going to determine how big your element is. Right? So let's see how we figure this out. So the first element that we're going to look at is going to be lithium. And what I'm going to address first with lithium is going to be the charge issue. So I'll put a star up here. And what we're going to do for lithium is we'll calculate the Z effective. Right? In order to keep room, I'm going to work down here. This could get kind of messy. So my Z effective for the lithium will be, okay, its atomic number is 3. This is the total protonic charge that's available to attract electrons. And we're going to subtract from that the core. Now, we need to know what the core is. So to generate that, what I'm going to do very quickly is write the electron configuration. So the configuration for lithium will be 1s2, 2s1. All right, and I'm going to circle, it would be better, the core. All right, these are your core electrons. And the electron that we find in 2s1, this is your valence. Or another way of looking at it is this is your surface electron. All right? How far this guy appears away from where the protons are is going to determine the diameter of this particular element. So what we're going to do is we're going to estimate essentially the charge available on this singular electron here because it is being screened by the 2 electrons which are in the core. I mean, if you think about this, if you were to put your eyeball right here, let's make an eyeball, and the eyeball is looking in this direction towards this singular electron, there's 2 electrons that are in the way. Another way of thinking about this is that these 2 electrons cancel 2 of the protonic charges that we've got in the nucleus. Now, that's a pretty loose way of looking at this, and it's not the best way, but it's reasonable for the moment. So the Z effective, the effective nuclear charge available to pull on this valence electron is going to be 3 minus 2 or plus 1. And I'm going to write that number down. So the Z effective for lithium is plus 1. All right, now, if we look at beryllium, we can utilize the same kind of argument. So for beryllium, the Z effective is going to be equal to 4, because that's the protonic charge, right? It's the atomic number. And we're going to be subtracting the core again. Remember that, let's see, for beryllium, let's see, where should I put this? I'll put it right here. The electron configuration is going to be 1s2, 2s2. So the core, I'll circle the core, is going to be the 1s2 electrons again. So this is your core. So we're going to take 4 minus 2, and we can see that the effective nuclear charge operating on the outermost electrons for beryllium is +2. Now, let's go ahead and calculate this for boron, and I think by then you should be able to see what the trend is going to be going across here for the amount of charge available to generate force of attraction on surface electrons. Remember that force of attraction, how hard those outer electrons are being pulled in towards the protons is going to determine the diameter essentially of the atom. All right, so let's see. The Z effective for boron is going to be 5 minus, all right, what's my electron configuration for this one? It will be, so for boron it's going to be 1s2, 2s2, 2p1. All right, now my core, once again, remember out here this is your valence. So the core once again is 1s2. So it's going to be 5 minus 2 or +3. So now you can see the trend. The effective nuclear charge for boron is +3 for carbon. It will be +4 for nitrogen. It will be +5 for oxygen, +6 for fluorine, +7. And for neon, it's going to be +8. So going back to Coulomb's law, look what's gone on here. See, here, this part in the top of the fraction is being represented in part by the effective nuclear charge, which you can see is clearly increasing. So I'm going to extend out my fraction bar. I'm going to put an arrow like this to indicate that as we go left to right across any period on the periodic table, your charge, so the numerator here, that part of this fraction is increasing as we move left to right. So the force of attraction on the surface electrons is going up as we go left to right across the periodic table. Now we need to address what's going on with the distance issue, this guy here. All right, and to do that I want to call your attention back over here to the diagram. So let's start again with let's go to lithium. All right, and I'm going to rewrite its electron configuration right here. 2s1. So for lithium, I'm going to go ahead and I'm going to put in the electrons in my diagram. This is what we got. All right, so we have, and this guy right here, I'll put an asterisk on it. That's our outermost electron. This is our surface right here. Now, when we move to beryllium, right, I think you'll see what I'm gonna where I'm going with this in a second. It's going to be 1s2, 2s2. So beryllium has got 2 electrons in energy level 1, but they don't have much to do with this other than screening protons. All right. Look where the next electron's going into to the energy level though, and I'm going to use a different color here. It's going to enter the 2s shell. So you can see that the distance did not change for the addition of the beryllium electron. So as we go left to right, the numerator is increasing, right, because our nuclear charge is significantly going up. But the distance in which that electron is being added has stayed the same. So that means that the force of attraction is going to increase between the surface electrons going from lithium to beryllium in a disproportional way, because the top of the fraction is going up, the bottom of the fraction is staying the same. Now when we move to boron, you can see we've got a situation that's going to change a little bit. It'll be a little bit different, because now you can see we have a new electron, and it's going to, I'll change the color, it's going to come in right here. And you say to yourself, well, ChemDoctor, look, the 2p series, you just got done telling us that it is a slightly higher energy than the 2s, which means that it has to be a slightly larger distance away from where the protons are. Yes, this is true, but this level of distance change is very small. So yeah, in this case, as we go from beryllium to boron, there's going to be a slight change in the distance square factor down here, but it's going to be a very small change. It's not the same as a change as if we were going from one energy level to the next. in that case, d squared would be changing in a remarkable way. In this case, it's hardly changing at all. So again, the major change going on is in the top of the fraction. So the force of attraction is still going to be increasing in a disproportional way. When we move to carbon, all right, let me get the electron configuration up for that, where it's going to be 1s2, 2s2, 2p2. You can see once again, when we add in that next electron, that it is being added to the same 2p shell as the boron electron. Obviously, it's going into its own subshell here, but there's no difference in distance between this electron and this electron from where it is away from those protons. So again, now your distance factor here is not changing. Yet, as we go from boron to carbon, you can see that the effective nuclear charge definitely went up again. So there's a disproportional change in the amount of charge as it increases, and the distance factor is staying constant. So I'm going to extend this out here, and I'm going to boil this down now. So we have in our numerator here, as we go left to right across the table, we have increasing charge, which is translating into increasing force of attraction, and we have essentially a distance factor that's remaining essentially constant. We have this little bump going on here as we go from the 2s into the 2p as we shift from beryllium into boron. But after that, you can see that each subsequent electron coming in is entering into the 2p shell, and each of these platforms is exactly the same distance away from the protons as the last electronic addition. All right. So the take-home message here is as we move left to right across any period on the periodic table, the force of attraction for the surface electrons is increasing while the distance essentially remains constant. The net result is that size decreases left to right across any period. And with that, I'm going to go ahead and close the presentation.